Hello, everyone, and welcome to our live session for today, June 20th, 2025. My name is Matthew. I work at the University of Arizona doing behind the scenes stuff. I'm part of the course staff for our online courses, and I'll be running things behind the scenes here today. Let's go over how these live sessions work. If you are new to the live sessions, welcome. If you are a regular viewer, we're glad to have you back. The way this works is please post your questions in the stream. I will moderate those, meaning I'll just grab those and put them in a list, and we'll choose from that list of questions. We try to go generally in the order that the questions are asked, but we do jump around to try and give everybody a chance to get one of their questions answered, and then also to give a variety of topics. So we want to, get as many people a chance to have their question addressed, and then we want to get from comets to cosmology, as Chris likes to say. Please ask your questions only once. I see them all as they come through. If I don't get your question immediately, it's because there are either some email questions or we're trying to give other people a chance to get in there. So Chris, why don't you welcome everyone, and then if you have a topic for us today, we can discuss that. Otherwise, we can get right to questions.
Okay, welcome everyone. We'll get started. So the topic, I do like to talk about a news story or current astronomy event at the lead-in here. The big news story is the Rubin telescope having its first data. So the Rubin Observatory, for those not familiar with it, is a very impressive survey telescope located in Chile, in Las Campanas. What's very important to us here at the University of Arizona, we made the primary mirror, the 6.5 meter mirror at our mirror lab, and the secondary mirror too. It's notable for having the largest digital camera ever commissioned for astronomy, because it's a wide field survey telescope, so it's 3 gigapixels. It takes 20 terabytes of data a night. It's surveying the sky and looking for variations. So it's going sort of to Hubble depth every 3 nights across the whole 2/3 of the sky visible from Chile in multiple filters, essentially comparing from one night to the next, 1 week to the next, 1 month to the next, looking for variations. And so it's going to pick up all sorts of variable objects. So it's a different type of science. The project used to call it celestial cinematography, which is a catchy phrase because most telescopes look deep and observe single objects or sets of objects. This is a survey telescope. That's really all that it does. It just takes data over and over again to quite impressive depth, but covering a very large area of sky. And it's going to produce amazing things. There's no question about it, because it's a new capability. It was funded in part by the National Science Foundation, the federal government, and the Department of Energy built the very impressive camera that sits behind it, really an important part of this telescope. And next week there's various ceremonies and news conferences associated with the first light data, or the first glimpse of the survey and what the quality of the data is. A very slight cloud on the horizon is the presence of all these Starlink constellations, or satellite constellations, which put bright streaks across the images of this kind of a deep survey telescope, and they actually compromise a significant fraction of the images. There are clever ways to sort of filter out moving satellites, but this problem is only going to get worse, because there are tens of thousands of satellites in low Earth orbit now, and they're not dim. They're quite bright when they catch sunlight and reflect it down to a telescope. But setting that aside, this telescope is going to look at cosmology, deep surveys of the universe, gravitational lensing, supernovae, near-Earth objects and distant objects in the Kuiper Belt, everything from the solar system to the very edge of the universe. It's a truly impressive telescope, and it's an international collaboration involving several countries and dozens of universities and research institutes across the United States. So look out for data and scientific results from this telescope in the weeks and months to come.
That is incredibly exciting. All right. Well, if people have questions about the that project, we will get to those. Right now, we'll start off with some questions that folks have posted in the chat. So the first question is from Ben Tennyson. Hello, Professor. My question is, why are dark matter and dark energy the dominant theories to explain those inconsistencies? Are there other explanations for those phenomena?
Yes, it's a wild west out in cosmology. We don't know what most of the universe is made of, and certainly there are alternative ideas. For example, for dark matter, one way of finessing dark matter and not needing a new form of matter that doesn't emit or radiate or absorb or interact with light at all is to alter the law of gravity. You can alter Newtonian gravity to do away with the need for dark matter. So there are some theoretical efforts underway to do new gravity theories. And this is not to replace general relativity, which is a very successful theory. This is the weak gravity that really applies through most of the universe. So that's a way of finessing or reconfiguring the idea of dark matter. Dark energy, it's even less clear how we should best proceed. Dark energy at the moment is the entity or agent, whatever you want to call it, that causes the universe to expand faster and faster, and gets the accelerating expansion of the universe is the main result that infers dark energy. But we really don't know what it is physically. So in a sense, dark energy is a frontier of the unknown. That term itself is just a placeholder for ignorance. So yes, there are many physical theories, dozens of papers written a year, hundreds actually a year, on the potential physical nature of dark energy, but astronomers don't have a lot of leads observationally.
Excellent, thank you. The next question is from Hirali Parmar, who asks, hi, Professor, can you explain curvature propulsion theory? I assume they mean the Alcubierre warp drive concept.
Yeah, I mean, the Alcubierre warp drive, which was an idea from 15 years or so ago, and it got some attention within NASA and other research groups looked at it, was a way of potentially accelerating spacecraft or physical object to relativistic speeds, which the energy requirement in conventional physics is extreme, and even potentially beyond the speed of light, which would break the laws of physics. It's essentially a way of distorting space-time so that you sort of surf a wave of space-time and accelerate a physical object that way. So it's a distortion, an extreme distortion of space-time. It is very much a theoretical idea. It was controversial at the time, and it's still controversial, and there's really no practical sense of how you might implement such an idea. So given that it sits in the realm of theory and it's somewhat contested theory, I'd say the jury is very much out on whether it's even a physically realistic possibility.
The next question is from Yang Pachankis, and I'm going to do my best to interpret this question, Yang, so if this is not what you're asking, then you can post a clarification. But the question is, if the cosmic microwave background becomes infinitesimally small, then how can we measure it using some other quantum detection method? I guess what is the future of the cosmic microwave background? Is it possible that it will get so faint and so small, or so difficult to detect that we won't be able to study it anymore?
So it is an interesting question about the future, the far future of the cosmic microwave background. Since it's the dilute radiation bath left over from the Big Bang, and since the universe is expanding at an accelerating rate, the temperature of the microwave background is going down steadily with time. Traditionally, it goes down proportionally to the redshift, and so the temperature at a redshift of 1,000, when the universe was 1,000 times smaller, it was 3,000 Kelvin, and now it's about 3 Kelvin. As the universe continues to expand, the temperature of the radiation will, of course, go down. It's microwaves now. It'll eventually become very long radio waves. So yes, both the intensity and the wavelength will go down. But what actually, in the end, will make it undetectable is not that. It's the fact that at some point in the very far future of an expanding universe, the wavelength of the microwave background radiation will exceed the horizon scale. In other words, the radiation will no longer be detectable because the wavelength is unobservable due to its being larger than our horizon scale. So our physical horizon of gathering information no longer includes it. That's very uncertain how you estimate how long ahead that is, but it's tens of billions of years.
The next question is from Wendy Traver, who sent an email. Are the things that we call constants, like Planck length and the speed of light in a vacuum, actually ultimate limits on our understanding of the cosmos, or could future research transcend these boundaries?
There are very few physical constants in nature, and we spend a lot of time, physicists spend quite a lot of time investigating whether or not they might vary. Some can be accessed with observations in cosmology and astronomy, and some are just subject to lab experiments. They include, of course, the Planck constant, the speed of light, the fine structure constant. Those are the three fundamental ones. And there are a handful of other constants which are really secondary. They're derivative from those fundamental ones. There's pretty good limits on the variation of those physical constants from the lab, and we don't see them varying over time. We have cosmological limits on the fine structure constant not changing over billions of years. So we should be keyed by observation here, because there are indeed physical theories where these constants can vary, but they're untested, and some are even untestable. But the observations so far speak to the constancy of the few physical fundamental constants we have in nature.
Excellent, thank you. The next question is from Bina M, who's on with us live. What are the current trends in space satellites, and what can we expect in the future?
I mean, the trends in satellites are, of course, for more and more of them to be launched into Earth orbit. Earth orbit is getting very crowded. The driver for this, of course, is telecommunications, and in particular the delivery of internet wirelessly or by satellite to the parts of the world that don't have internet. In the Western world, 80 or 90% of people have internet, and there's no thought about the internet. It's ubiquitous. But if you go to Africa, especially some parts of Asia and South America, they don't all have the internet. So these telecommunication satellites, large numbers of them, are designed to give a dense network of delivery points for wireless internet. They're also used for communication, for general communication purposes, telecommunication for radio and TV and so on. So these drivers economically are growing. So the satellite business is $1 trillion a year business, more or less, or it's headed towards that. And it's been growing year on year 6 or 8%, so very rapid growth. And it's also a large number of satellites. The number of players, famously Starlink puts up many satellites, but Amazon is involved, and other large tech companies all have their own reasons for creating networks of satellites. And sometimes countries want their own. China, for example, wants their own set of satellites to produce their own version of a GPS system, independent of the one that we already have. All of these things are creating a logjam in space, and it's having some effect now because low Earth orbit is full of debris, it's full of collision-making objects. The shrapnel and small particles then destroy other satellites, and we're within sight of low Earth orbit becoming unusable if we continue to launch satellites at the rate they're being launched.
Excellent. The next question is from Ben Tennyson, who asks, why does it seem flat when relativity allows curvature?
Yes, general relativity is in fact premised on mass and energy causing curvature of space and time. So curvature is sort of built into the theory. But in the situation of the universe, which is extremely large and old and has been expanding for almost 14 billion years, that curvature has been stretched out to an incredibly low level. So there are measurements that were done first 20 years ago with microwave background observations, which measure the space-time curvature on large scales, essentially measuring the way the universe curves over the whole history of microwaves traveling through space since the Big Bang. And the limits on curvature are quite extreme. The curvature of the global space-time is less than 1% deviation from flat. So space-time is flat, and fundamentally it's because the universe underwent an extremely rapid period of early inflation, which flattened space-time substantially. and led to it being essentially flat now, and then a more sedate cosmic expansion since then, which just continues to make it even closer to flat. You'd have to have large concentrations of mass or energy to deviate from flatness, and the only places we know that happens is for black holes and neutron stars. But on these large scales, there's nothing to curve space-time.
The next question is from Dawn of the Force, who is on with us live, who asks, why have we stopped building new and similar missions to the Voyager spacecraft to send them out past, through on these tours through the solar system or to, distant solar system locations, now that we have such advanced technology?
It's a good question. The outer solar system satellites had their heyday, had their the peak period in the 1970s and 1980s, was especially with the Pioneer, the twin Pioneers, the twin Voyagers, and we got our tour of the outer planets from those. So why are we not doing that now? There's several reasons. One is that NASA's budget is very constrained. NASA's budget now, in real terms, adjusted for inflation, is 2 times lower than it was when the Voyagers were planned and launched. So NASA has to do more with less, and these are expensive missions. They're all multi-billion-dollar missions if you launch a new one. It's not that we've learned everything we need to know about the outer solar system, by no means. Cassini was the last major mission, multi-billion-dollar mission, to visit Saturn and its moons. So that's the kind of mission we want more of. So they're expensive, and they also take a very long time. So you need a long commitment. The people involved have to commit to a decade of planning and construction. To get to the outer solar system takes years. Analyzing the data, more years. So these are multi-decade commitments of the scientists involved, and that, of course, also requires continuity of funding. It's not something you can knock up a satellite and put it into orbit and get your data within a year. So the time scale also goes against having more of these missions. And then planetary science is only one community of interest for science, and it competes and has to compete with astrobiology and cosmology and normal stellar physics and other areas. So the funding is split multiple ways, and people studying the planets are only going to get some fraction of that funding. So the funding limitation is also another reason.
The next question is from Ayush, who asks, in cosmic inflation theory, we talk about the accelerated expansion, and it seems to be explained fairly well, but what started the expansion at first?
Well, the Big Bang is the original expansion of the universe 13.8 billion years ago, and the theory does not contain an explanation. So the simple answer to the question is we don't know, because the Big Bang theory is a physical description of the evolution of a universe from a very hot, dense early phase, possibly a singularity. But the theory itself contains no information or speculation or idea about how it started. So that's the simple answer. We don't know. Big Bang does not tell us what came before or what caused it.
The next question is from Adrian, who is on live. Is it possible that the missing matter in the universe might be hydrogen gas in and surrounding galaxies?
The missing mass has been characterized as the mass that we don't see in the form of baryons or normal particles. So we don't want to get confused here between normal matter and dark matter. So setting aside dark matter, which is another issue, there's also the question of where the normal matter of the universe is, because we only see about 10% of what we think to be the amount of normal matter in all the visible stars in all the galaxies. How do we know that? Because the Big Bang Theory contains as one of its few parameters the amount of baryonic material, which is in the theory about 4% of closure density. And we've observed 10 times less than that in all stars and galaxies. So people have been looking for normal baryons, that is to say protons and electrons, mostly hydrogen and helium, for a long time. That question is essentially solved now. X-ray telescopes started to solve it because the intergalactic medium is a very hot, diffuse medium at a temperature of millions of Kelvin, and so it emits or radiates in X-rays. And recently, low-frequency radio observations have also diagnose the intergalactic medium. This is a result from the last month or so. And between the X-ray and the radio observations, they've pretty definitively shown that most of these missing baryons, or the missing normal matter in the universe that's not in the form of stars and galaxies, visible stuff, is in a very low, a very diffuse, low density gas that's also at a very high temperature. So this is essentially a solved problem now.
The next question is from Dan Cooper, who would like to know, do you know what's going on with SpaceX? Another rocket blew up on the launch pad yesterday or the day before, and that, you know, they seem to be having some difficulties right now.
Yeah, SpaceX is clearly going through a rough patch. I think they've had catastrophic or serious explosive failures of 3 out of their last 4 launches. This was the 10th test of the Starship, and it was an explosion on the ground. It was the explosion of a compressed nitrogen tank, I think, which decompressed explosively and led to a fireball. The video is quite spectacular. No one was hurt, luckily. So yeah, SpaceX is having a rough patch. The testing and evolution of the Starship depends on improvements, incremental improvements from one launch to the next. And for the first half dozen launches, even though a couple of those were failures, you could claim that they learned each time, made improvements, and then did better the next time. Getting into orbit or returning the booster and catching it, those were good successes. But since then, things have been a bit rough and ready, and I don't know how this is going to go. SpaceX will keep up a very tight, rapid cadence of launches. I'm sure there'll be another 6 or 8 or maybe 10 in the rest of the year. But they need to start showing better progress from one launch to the next to have any hope of meeting the very aggressive timeline Elon Musk has set to getting to Mars.
The next question is from Sira, who sent an email. I've always had a passion and interest in reading about energy and extraterrestrial life. NASA continues to make significant discoveries about exoplanets, but where are the aliens? Is there something that we're missing? Interstellar communication doesn't seem to be working at the moment. Why not find another technique?
So where are the aliens? A good question. It was first posed actually scientifically by Enrico Fermi in 1950, a long time ago. Where are they, he asked, even simpler question. So there are obvious answers to this, and people have written books and articles about this extensively. I mean, one answer is there are no aliens, that even if the universe has life in it, it may be essentially microbial, that it's very, very, very unlikely, or it takes a very long time for life to evolve from microbes to complex intelligent creatures, especially those with technology. And maybe almost none get technology, or they become unstable and self-destruct, all sorts of possibilities. So it's absolutely possible that there's no one there to talk to, and no one trying to talk to us. The mode of communication, of course, is important. So if we're trying to communicate, are we doing it the right way? Radio waves have been used historically because radio waves are cheap in energy. They travel freely through space, penetrate large regions, which optical light does not. So they make a lot of sense as a mode of communication. But are they the only way aliens would communicate? I don't think so. So we make assumptions anytime we use a mode of communication. But in the end, this is a niche of astronomy. This is a subject, SETI, and an observational initiative that really only spends few tens of millions of dollars a year. So it's less than 1% of the global astronomy effort, if you like. So it's a very small niche, and maybe that's part of the reason we're not making progress, because we're not devoting a lot of resources to it.
The next question is from Angelo, who asks, are there any concerns? Well, you said, and you've addressed this a little bit twice, but we can talk about it specifically. Are there any concerns to astronomy with new internet satellites being deployed every year? Can you talk a little bit about how it's being addressed? You talked about there are techniques for dealing with this, but can you talk a little bit about more specifics?
Astronomers have a limited leverage on the commercial sector. They are driven by business models and profit motives. They want to make money for themselves and their shareholders. So astronomers really don't have any way to intervene in that. But it's not in the interest of these companies to be bad actors in space. So I think they have some incentive to try and make things better. And Starlink, particularly, and some of the other constellation builders are talking to professional astronomer groups. Starlink did change their satellite design. They used a less reflect. They're already coating their satellites essentially in black paint, but they used an even more absorptive or less reflective form of paint, trying to reduce the reflected light from the satellites, and they make their footprint physically smaller as well. So that was a concession and a significant effort that they did, and it seems to have made an improvement. So there is dialogue between astronomers and the companies putting up these satellites, which hopefully will moderate some of the worst inclinations. It's also worth noting that many of these satellites in a very low Earth orbit do not pose a accumulating problem because they're in very low but significant density rarefied regions of the atmosphere where there's drag, and so they only last 5 to 7 years in orbit before they decelerate or pulled into the atmosphere and burn up harmlessly. They don't impact the Earth's surface. So some of the part of the problem takes care of itself.
Excellent. The next question is from one of our live participants. Vlad asks, what is the current theory or leading theory that could or might replace the Big Bang theory?
There really isn't a truly viable alternative to the Big Bang theory, and it's easy to see why, because the Big Bang theory has been around for quite a long time. The Big Bang theory was developed in the 1940s and was cemented and became the dominant theory in the mid-1960s with the discovery of the microwave background. So that's a pretty mature theory, a lot of observational support, and basically any alternative theory would have a very high bar to clear, because an alternative theory has to explain why the universe is bathed in microwaves with a temperature of 3 Kelvin. It has to explain why the very light elements have particular abundances, and in the Big Bang that comes in the first few minutes. And the Big Bang and the theory, of course, has to explain the expansion of the universe, the nature of the expansion, and the history of the expansion, and put an age on the universe. And there are no completely or radically different theories that can do all those things. So I'd say at the moment there is no viable Big Bang theory. Now, it's a little circularity to that argument, because when theories get very successful, there's strong disincentives from even maverick theorists in developing a new theory. Why would you waste your time, others might say. So, it's only when a field is dynamic and uncertain, as it is, say, with dark energy, that people are busy making different theories. On the basic Big Bang itself, there are not many people doing that.
The next question is from one of our live participants. Faisal asks, the number of chemical elements found in nature in the periodic table is 118. Is the presence of all these elements required for the diversity of life on other planets?
That's a good question. So what are the life elements? The core life elements are a very modest number. It's hydrogen, carbon, nitrogen, and oxygen. So you can generate almost all the biogenic compounds, the biomolecules of life, from these basic elements. Obviously, hydrocarbons are the basic form of chemistry. And then you can add oxygen and nitrogen. If you go beyond those 4, then there are other important, there are probably another 6 or 7 elements you'd add to the table. Certainly sulfur would be one of those, calcium would be one, sodium, and particularly phosphorus. Phosphorus is very key to life because it's part of the energy storing and energy producing molecule ATP. So phosphorus is an essential one. And then you get down to trace elements. So life needs those dozen elements, all life does. But biology, as we understand it, and when you look at it, involves about 24 elements. And that second dozen elements, even though they have very low concentrations, selenium would be one example, they're quite obscure elements, those elements are actually quite important. They have biochemical uses. Now, it's not clear whether every form of biology beyond the Earth would be based on all those elements. So the sort of low abundance elements that are part of life processes may be contingent. They may be not truly necessary to have biology. But I think the carbon, nitrogen, oxygen, and hydrogen are truly fundamental to any form of biology anywhere in the universe.
The next question is from Fact Grace, who's on with us live. Hello, Professor. I am curious about the relationship between space and time. Is time ruling space, or is space ruling time?
It's an interesting question, and philosophers and physicists still wrestle with it, the nature of time itself. Because Einstein's theory of general relativity, which couples these two things into a hybrid entity called space-time, so it mathematically couples the time dimension to 3 dimensions of space, it doesn't truly explain what time is. It does, of course, lead to some interesting consequences, because the presence of mass and energy can distort time as well as it distorts space. But again, these are just physical effects within a physical theory. They don't say fundamentally what time is, why, for example, time is unidirectional and there's an arrow to time. Is there a quantized nature of time? So space is quantized at some level, at the fundamental level. We don't actually know if time is quantized or if it's smooth and continuous right down to the quantum limit. So there's some big enigmas about time that are not addressed by current physical theories, which means theorists are still speculating.
The next question is from Ben Tennyson, who would like to know, do you know, or what do you think are the best, or is the best amateur research project? Do you think that volunteering in Galaxy Zoo will be considered as good as, they say ECA. I'm not familiar with ECA, but can you talk a little bit about some of these amateur research projects and which ones you think are the most valuable?
Yeah, Galaxy Zoo was the origination of citizen science in astronomy. So it's been going a long time, and we still have impressive numbers of surveys to sift through, and there's still things we don't know about galaxies. I would say it's not maybe the now in the mature realm of citizen science. I would say it's maybe not the best thing to get involved in, because most of the easy work has been done, and now we're into more esoteric things, looking for very bizarre, diffuse, or rare forms of galaxies. The two areas that are still very active and which are good entry points are, one is on exoplanets, so it's still possible to look through the messy and complicated data that leads to transit detections of exoplanets and possibly even exomoons, and for citizen science to get involved in that analysis. That's an interesting area. And the second one is supernovae. Supernovae are by nature unpredictable, so they go off about once per century per galaxy, and amateur astronomers with even 10-inch telescopes can observe thousands of galaxies and see supernovae going off. And then professionals have data that amateurs or citizen scientists can study. So I think supernova work is always going to be a popular one, and it's a way to get your feet wet in citizen science.
Okay. They also, I guess, ECA meant extracurricular activities. Are there other ways to contribute to research other than that? Okay. The next question for today is going to be from Bhavika, who asks, do black holes really exist? I recently read a science book which made the claim that true mathematical black holes do not exist. Are there possible alternative explanations for black hole phenomena?
It's an interesting question, because black holes are a sort of mature subject in astrophysics, and we have observations of stellar mass black holes, and now quite good observations, including a couple of images from the Event Horizon Telescope of supermassive black holes. And it's very hard to explain those observations by any other theory. So generally, I would say the evidence that black holes exist is pretty strong. We also know their prediction of general relativity, a very successful gravity theory. However, the door is open on some areas, especially on the massive black holes. There are theorists who've proposed that you can explain the observations in galactic nuclei with supermassive stars, single supermassive stars. So they're not formally black holes. They will form. Of course, they can self-destruct. They're not going to be stable. They're not going to live a long time because they're supermassive. And then in a dense region, they reform and explode and reform and so on. And there's theorizing that says that in the center of a galaxy, you don't inevitably have to have a supermassive black hole as the endpoint of the evolution. You could have supermassive stars. So that's an interesting idea that's on the table, and hopefully it'll be tested by astronomers in the next few years.
Thank you. The next question is from an email. Kathy Donnelly would like to know, I just completed a 200 level college physics course in galaxies and cosmology, and I found the cosmology portion to be utterly fascinating, especially the development of the early universe. Could you maybe recommend any books to continue learning about this area?
Right. Not off the top of my head. It's a pretty active area, so there are a lot of good cosmology books. If you're talking about the semi-technical level, at the level of undergraduates studying astronomy and physics, there are a number of books. Carolyn Ostley is the sort of foundational textbook that covers all of astrophysics and includes galaxies and cosmology. Linda Spark had a book on galaxies that I think is now in a second edition or a third edition, and that's Spark and Gallagher are the two authors, and that's a really good book on galaxies that includes some cosmology. So there are a few books out there, and then there's some very esoteric, theoretical, graduate level cosmology books, but that's probably not what you're interested in.
Thank you. The next question is from Ranjan, who asks, how do current observational limits shape our understanding of dark matter and dark energy, and what would it take to move from inference to direct detection?
Our observations of dark matter definitely shape a view of it, but it's interestingly difficult to constrain the nature of dark matter. For example, there are theories that propose that the dark matter particle might be self-interacting. So although dark matter doesn't interact with radiation, dark matter particles interacting with each other could lead to cooperative effects that will distinguish it from dark matter particles that are essentially aloof from each other, except by the gravity they exert. So self-interacting dark matter is one idea that's on the table, and people are wondering how to test that. For dark energy, there's no single idea on the table. There are many ideas. There's not enough consensus as to what the plausible explanation is to pick one out. So there are these observations that are possibly going to help, but for dark matter in particular, since we've eliminated so many possibilities and are almost certainly left with a fundamental particle, the true resolution will probably come from lab experiments rather than astronomy observations. In other words, the dozen or so experiments that are trying to detect the fundamental dark matter particle, typically down deep mines with various sorts of detectors, they may be the decisive element in figuring out this enigma.
The next question is from one of our live participants. So you talked a little bit about the limits of our knowledge about what caused inflation, but can you talk a little bit about what caused the rapid inflation rate to decrease, and then what caused it to begin increasing again?
So inflation is a period of time very briefly after the Big Bang, 10 to the minus 35 seconds to about 10 to the minus 32 seconds after the Big Bang. Hard to imagine those numbers. When the inflaton field, so it's a field that causes inflation, it's associated potentially with some grand unification of all the four forces. When that field went into an unstable mode where it propagated through space-time, causing it to exponentially expand. That's a very rapid doubling. So the universe went from smaller than a subatomic particle to sort of macroscopic size of a meter or so in this incredibly short period of time. And the cause of that, we don't know. It's built into what the inflaton field is, and nobody knows what that field is. The exit of inflation is also not clear because for inflationary models for the first 10, 20 years of the theory, starting in 1980, it was called the graceful exit problem. There was a really hard job in theorizing an inflationary field that would have a graceful exit into a smoothly expanding universe of the type we see now, rather than just a catastrophic ending or continued exponential expansion until you have no universe at all. It's just all spread out impossibly thin and you never get galaxies and stars. So the answer is these things are not yet resolved because we don't know what the field that drove inflation initially is, and what that field would look like now if we were trying to investigate it.
The next question is from Ernest, who's on with us live, who would like to know, can you explain string theory in simple terms?
No, nobody can explain string theory in simple terms. There is, of course, in the famous Science and or Subject X, Y, and Z for Dummies series, there's a book called String Theory for Dummies. So I read with the yellow cover. They're very familiar books. I recommend that. I borrowed it and read it off someone. It's a good book. So that's the way to get this, and I can't do it in a short Q&A here. But string theory is basically a frontier physics theory to hypothesize that beyond the level of particles that we talk about, electrons, protons, neutrons, quarks, everything is based on fundamental entities that are one-dimensional, that are on a tiny scale, 30 orders of magnitude smaller than the size of, say, a proton, and that only manifest at extraordinarily high energies. And the only way to make a viable theory of these strings is if space-time is multidimensional, which is to say potentially 9 or 10 dimensions of space plus 1 of time. Those are the very bare bones of string theory. It's intensely mathematical. It's considered to be very beautiful mathematics, which is why people are drawn to it. It's very difficult to test because it operates on energies and physical scales that are really not accessible to experiment. And so string theory is essentially sitting in limbo, waiting for some affirmation experimentally that it's a valid theory of nature.
Excellent, thank you very much. The next question is from Hernan Reyes, who sent an email about Life 2.0. The question is, shouldn't research for Life 2.0 be focused on exoplanets that are reasonably, quote, not too far away? If we were to find a biosignature too far away, then it would take hundreds of years to get information back and forth if we wanted to explore it. What do you think is a reasonable radius from the Earth to sort of look for signatures of life that we might be able to explore in a reasonable amount of time? And are there planets in that radius?
So we are actually looking in our cosmic neighborhood. So almost all the exoplanets that have been found so far, 7,000 or so, are within a few thousand light years, and the median distance is a few hundred light years. And the Milky Way is 100,000 light years across, so these are in our backyard. So already almost all the exoplanets are in a fairly proximate region of the galaxy. It is true that at distances of hundreds of light years, if you wanted to have communication experiments, that's going to take centuries, and if you wanted to travel, that's just not on the cards. The TESS satellite, which is the successor to Kepler and complemented Kepler, TESS has had as its main focus all sky picking the nearest exoplanets that are potentially good for life detection experiments. So TESS's targets are all within a few dozen light years, and that's interesting. It includes Proxima Centauri, of course, the nearest star to the sun. So the TESS candidates for biomarker experiments or life detection experiments are the top list, the hot list, if you like, that astronomers are focusing on. And they are really nearby. They're the nearest stars to the sun.
The next question is, we have two of the same kind of question from Ben and Arthur, who would like to know, is our universe, or is it possible that our universe could be inside a black hole and that another universe could be inside another black hole? And are there any ways of testing or ruling this out as a possibility?
So the speculation of a sort of hierarchical universe where our observable universe is part of an even larger system, those theories still have traction because we have a horizon, because the standard cosmology includes a limit to our vision. In the rapidly expanding universe, the initial expansion was so rapid that we know there are regions of space and time that we can't observe, and we'd have to wait to observe till the light became visible to us. So right away, we know the observable universe is not the entire universe. And given that, we don't know how much larger the physical universe is. And so it's entirely possible that on an even larger scale, we're sitting in some kind of an event horizon. Maybe event horizon is not the best term, though, and the idea of the entire universe residing within a black hole really pushes the definition and understanding of black holes, so I don't think that's the best way to put it. But having a cosmic landscape that involves a hierarchy of universes, that's certainly plausible, and it's going to be very interesting to see if we can test that idea.
The next question is from Dave McKenzie, who sent an email. Are there any updates on the development of fusion energy, and will the cuts to science funding possibly be a problem for further research and development and advancement with that?
So fusion research has been a frustrating endeavor for those involved in it. It does only get a modest amount of funding, really, a few $100 million a year in the United States, maybe $1 billion a year worldwide. But progress has been slow. It's a very intensely technical, difficult problem. In the US, break-even has been reached on fusion reactions where you get net positive energy for a significant fraction of a second, or I think maybe 10 or 20 seconds is now the record. That's quite impressive. That's nothing like having a working reactor, though. So that's how difficult it is to progress, and that progress itself has only been made in the last few years. The research on different fusion reactor designs continues. We still use the tokamak, the donut toroidal model, but there are other, at Los Alamos they use pellets which are ignited by lasers all pointing at the center, so that's laser ignition. So there are various models for fusion reactors. But I would say there's no immediate revolution on the horizon, and the people involved in this have moderated their expectations for when the first viable fusion reactor might be, and it's decades away.
The next question is from Eric Autumn, who asks, what progress is there in identifying a graviton particle?
No progress, really, that I've heard in the last few years. Graviton is the hypothetical particle. It's the counterpoint of gravity, and that's from the standard model of particle physics, where you have particles as mediators or carriers of the four forces. So electromagnetism is carried by photons. The weak nuclear force responsible for radioactivity is carried by the W and Z bosons, and the strong nuclear force is carried by the quarks. So these are the force carriers, and those are three of the four fundamental forces, and the fourth is gravity on a very much weaker scale. And so the properties of the graviton, apart from the fact that we know that it's a spin 2 particle or a boson, are really hard to determine. And detection of the boson or that graviton as a particle has not succeeded. And it's actually very difficult to design experiments to prove that you're dealing with a particle rather than just with a field.
The next question is from one of our live participants. Do you believe that matter-antimatter propulsion would be a good bet for exploring nearby solar systems sometime in the future?
Well, antimatter drive is a science fictional idea, but it's not entirely science fiction because antimatter exists and can be created, and we know that matter-antimatter annihilation is the most efficient way to get energy. Chemical energy, which the Earth still mostly runs on, is 100 million times less efficient than fission and fusion, and antimatter matter annihilation is 100 times more efficient than fission or fusion. So it's the most efficient energy possible. The trouble is you need to harness antimatter, and you need to harness enough of it or create it continuously enough to power that reaction. And the technology to do that is formidably difficult. Huge high-energy accelerators, immovable objects the size of cities, costing billions of dollars, are required to make even tiny amounts of antimatter. So we would have to have antimatter factories creating substantial amounts of it. We'd have to have new types of containment systems to create a rocket for it, and of course there'd have to be a lot of testing. So it's dangerous to put a timescale on anything, but for antimatter rocketry, antimatter travel using that technology, I don't think we're talking decades. I think we're talking a century or more.
The next question is from Ranjan, who asks, do you think that the discovery of life elsewhere would change how we approach fundamental questions about the universe, or do you think it would reshape our philosophical perspective?
It would be profound and earth-shaking news to know that we're not alone in the universe. It would reshape science. It would, of course, reshape biology, because we'd suddenly realize that there was not one biological experiment in the universe, but potentially many, and we'd have a general theory of biology at some point, which we don't have at the moment. We just have a biology theory of this planet. We don't know how general those principles are. So it would absolutely profoundly change biology, it would change astronomy, and yes, it would affect sociology and cultural issues, affect our sense of self, to know whether we're the smartest people on the block, if you like, or not the smartest, and the universe is filled with intelligent life and we're not even that special, another version of the Copernican realization. So there's no question that it would be a culturally earth-shaking event to detect intelligent life elsewhere.
And the next question is from Shalabi, who asks, do you know anything about the current research areas in astrochemistry and planetary nebula? And do you know if any of those fields would be a good choice based on impact and future opportunities for someone in the astronomy field?
Yeah, astrochemistry is a niche of astronomy. It's a subsidiary subject, and it's interdisciplinary, of course. You need significant chemistry training to do it. And yeah, there are some growth areas and very interesting observations. Observationally, it's driven by the types of telescopes that can detect molecular transitions, so chemistry in space, and these are at long wavelengths, they're low energy transitions and rotations, and so it's radio astronomy and millimeter astronomy. So the progress of those fields has led to a lot of observational possibilities, so that's good. And then our theoretical understanding is also progressing. So one area that's very interesting for astrochemistry is investigating solar nebula, protoplanetary disks, and sort of understanding how the chemistry and geology of planet formation occurred, and where the life-giving elements came from, and how they were distributed, and how they ended up on terrestrial planets. So within the study of exoplanets and solar systems elsewhere, there's very exciting work being done on astrochemistry. And then some astrochemistry applies just to the interstellar medium, not places where stars or planets are forming necessarily, but dark and dense molecular clouds, where we've seen over 150 different molecules, ranging with numbers of atoms up to 20 or 22, I think. So that's an active area too. So I think both observationally and theoretically, astrochemistry is a really rapidly moving and exciting subject.
Next question is from Thomas Rees, who sent an email. What is the obsession with some people on trying to find Planet 9?
It's interesting. It's been going quite a while. Maybe it's a compensating thing about having demoted Pluto in 1995, so now we need a substitute. But it's always been an idea. There have been two ideas. There's first of all the idea that there was an interior planet to Mercury, or a planet in the very inner solar system that sort of just lurked on the opposite side of the sun from us, and so it's hard to detect. That idea of a Planet 9 or Planet X, that's been pretty much debunked now. There's no observational evidence for that. But for an outermost planet, Planet 9, the ninth planet in the solar system, beyond the four gas giants and the four terrestrial planets, that's a very active area of search, and it's a lot of work to search the Kuiper Belt, the region of known rocky objects 40 to 80 astronomical units from the sun, to find the biggest of those, because it's very far away, and these objects receive very little sunlight, so they reflect very little back, and so they're very dim. And they move quite slowly because they're so far from the sun, so you have to get a lot of data to track the motion of something. So that field is going to continue, and I think it's just partly because it's so easy to hide a Pluto-sized or even bigger-sized object out in the Kuiper Belt, that it lives on the fact that it must exist and there must be a substantial planet out there. So it's the difficulty of ruling it out, I think, that lets this subject live on.
The next question is from Newton Baba, who says, in some books I've heard of 10 spatial dimensions. Is that possible, and what would that really be like or look like?
So the 10 spatial dimensions comes from string theory, which is this fundamental theory that posits that beyond the level or below the level of normal particles, electrons, quarks, neutrinos, etc., are one-dimensional entities called strings, whose physical scale is 30 or so orders of magnitude smaller than the size of a proton, and whose energy scale is the same number of orders of magnitude higher than the temperatures of the terrestrial and conventional universe. That 10 number of dimensions comes from the mathematics of the theory. String theory naturally incorporates multiple dimensions. And in this situation, if string theory applies, then those missing dimensions would be hidden. Those hidden dimensions would be compactified, to use the word from the field, onto an incredibly small scale, far smaller than a subatomic particle. And so that's why those hidden dimensions become invisible to us, or hidden. And it's very hard to prove their existence. So this is an untested and unproven theory.
All right, it is 10:59. I think we have time for one final question for today. The final question comes from email, and it is, do we know if the various types of photons have maintained the same wavelength ranges over cosmic time? And in particular, has the visual range stayed constant?
So the nature of photons over cosmic time is interesting, because photons in space are traveling through an expanding medium, expanding space-time. And so they're stretched with the expansion. So the simple answer is that the photons in the universe have all been changing their wavelength continuously because of the expansion of the universe. You can think of the expansion of space-time as stretching everything within it, including an electromagnetic wave. And so the photons that are currently microwaves that we see as evidence of the Big Bang were, when they were first emitted, visible radiation at a temperature of 3,000 Kelvin. So they were light waves, and now they've become microwaves, and that will continue to even longer wavelengths. So all the photons in the universe are subject to this degradation in energy and extension or expansion in wavelength due to the expansion of the universe. So there will always probably be optical light in the universe, but that optical light will gradually turn into infrared light and radio waves, and new forms of radiation will be stretched from ultraviolet and X-rays into visible light. So the good thing about this is that optical light will probably always exist in some form. That's a good session. I will actually ask and answer a final question to sort of bracket the initial one that I framed relating to the press release of next week. And the question I will ask and answer is, who is Vera Rubin? Because the telescope that's named after him was originally called the Large Synoptic Survey Telescope. So it was called LSST by its acronym for several decades while it was being initially planned and built. And then some not too many years ago, it was decided to rename that telescope after Vera Rubin. Well, that's a huge honor, of course, for any astronomer to have this enormous multi-billion-dollar facility named after them. So who was Vera Rubin? Vera Rubin was essentially the observational architect of dark matter. She worked at the Carnegie observatories for most of her career. As a young woman in astronomy coming up in the middle part of the 20th century, she suffered intense prejudice and suffered a lot of obstacles that many women in astronomy faced then, more strongly than they do now, but they still exist now too. And she persevered through all of those. Well, she had to persevere through a second set of obstacles, because in her measurements of galaxies and their rotation, she saw signs of dark material that had to be there to cause the rotation being as fast as it was. It's a very controversial idea, because there was no idea of dark matter back then in the 1970s. And it was unpopular. And she, as a young researcher, no longer a graduate student, I think she was a postdoc, she was given a lot of disrespect and skepticism. She had collaborators, of course. She was part of a small team, and eventually people came around to her point of view. And so she persevered through the 70s and 80s until sort of the field sort of caught up with her and realized, well, there really is this dark stuff there in galaxies, and the galaxy rotation curve is still one of the best ways to diagnose it. And so she was the pioneer of that aspect, very important aspect of modern cosmology, which is this idea that the universe is filled with dark stuff, dark matter. Now, she never lived to see what dark matter is, and we still don't know what it is. But she had a long and illustrious career, and I knew her pretty well back when she was retired and finishing her career. So she is indeed a very worthy recipient of the honor of having this huge telescope named after her. That's all for today. We have another one on the books. I don't remember when it is, but Matthew can probably say, and thank you for all attending, and thanks to Matthew for facilitating.
Yes, our next one is currently scheduled for 4 weeks from today. We have a bit of a break in here due to some travel. So the next one is July 17th. And that's a Thursday. So we will see you all hopefully back here then. And if you would like to receive information about upcoming live sessions, if you scroll to the top of the chat, there's a link that you can grab, and you can add our astronomy live session calendar to your Google Calendar, or you can join our listserv, our Google listserv, and we will send out announcements about upcoming live sessions. So thank you all. Also follow our channel, obviously. Follow and click that bell icon. Click the like button, because that helps boost the signal for our live sessions and gets those out there. So thank you all so much for joining us today. We will see you all again on Thursday, July 17th. Take care.